Good evening, everyone. Welcome to the first Coast Guard Tech Talks workshop. These workshops are jointly sponsored by the United States Coast Guard, the Coast Guard Auxiliary, and the Boy Scouts of America's Sea Scout program. My name is Bruce Johnson, and I serve as the Chief of the Coast Guard Auxiliary's Youth Programs Division. Your co-host is Josh Gilliland, Chair of the National Sea Scout Marketing Team. Josh will be coordinating your questions in the third part of the program. Coast Guard Tech Talks will be held monthly on the fourth Tuesday of the month at 2100 Eastern, 2000 Central, 1900 Mountain, and 1800 Pacific time. Each program will focus on a single science, technology, engineering, and mathematics, or STEM topic. These topics are chosen to support the Sea Scout Advancement Program. Tonight's topic is maritime weather. The speaker and organizer of Coast Guard Tech Talks is Lieutenant John DeCastra, U.S. Coast Guard. Lieutenant DeCastra, or JD to his friends, is a Coast Guard rotary wing aviator stationed at Air Station Atlantic City, New Jersey. He holds a Bachelor of Science degree from Auburn University, where he also began his Coast Guard career in the Auxiliary University program. He's been a Coast Guard auxiliary since 2010 and has served as a National Safe Boating Week coordinator. One last thing, we've muted your microphones to make it easier for everyone to hear. If you have questions, please type them in the chat box. Josh will be monitoring the chat and will be sure to leave time to answer your questions. So let's welcome JD to Coast Guard Tech Talks. Take it away, JD.
Excellent. Thank you for the wonderful introduction. Welcome, everyone. Good evening, good afternoon, maybe even good morning. As Bruce Johnson said, I'm JD DeCastro, Lieutenant in the Coast Guard, and I'm not going to dive much more into that because I want to make sure I get you the information. So we're just going to jump right into it. So today we're going to be talking about weather, and we're going to do 4 or 5 main things. First one, we're going to do a little bit of the science behind the weather. That way, when I start talking about things like deepening lows, frontal discontinuities, you're not like, what in the world are you talking about? So we all have a similar vocabulary or similar knowledge to dive in. Then we're going to talk about measuring equipment, things that we do, barometers, thermometers, anemometers, weathervanes, etc. Then we're going to talk a little bit about how a forecast is made. By no means is this going to be comprehensive. However, we do want to talk a little bit about how we get to where we get. And then we're actually going to dive into some weather forecasts. We're going to be using marine forecast, aviation forecast, and then just a normal forecast. And then finally, we're actually going to make a weather station. So let's see if I can do this. All right, let me try and share my screen with y'all. Excellent. And hopefully y'all are all seeing my screen. So I'm actually going to use real-time weather data for this. And I'm going to kind of walk us through how we get there. So the first one we're going to use is the National Weather Service. We're going to go down to the National Forecast Maps, and we're going to look at the surface analysis chart to kind of talk about the science behind the weather. And the first thing which we're going to be looking at is an air mass. So what exactly is an air mass? Exactly what it sounds like, a giant mass of air that all has very similar properties. Temperature, humidity, pressure is roughly all the same. And when I mean all the same, it's not going to be 72 degrees across the entirety of the air mass, but it's going to be roughly that. And when you compare it to another air mass, it will definitely be the same. So for example, one air mass might be an average of 72. It might be abutting an air mass that's an average of 40. 70 compared to 40, even if it's 69, 68, it's still closer to 70 than 40. So we have 4 main types of air masses, and those are based off of where they are geographically. So we have polar and tropical, and then we have maritime and continental. So you could have a polar continental, which would come from the middle of Canada, or you could have a polar maritime coming off the Bering Sea, vice versa. Tropical continental, vice tropical polar. And that's essentially what an air mass is, a giant chunk of air with roughly the same. And based off of two air masses is where we get into our next thing called a front. So a front, whenever you hear someone use the term front, there are a couple different types of fronts. We have a cold front, which is going to be this area right here, where a cold air mass right here is overtaking a relatively warm air mass. You're then going to have a warm front, which at the moment looks like the only warm front is based off of right here. So right here, this is what a warm front looks like. You're having a warm air mass overtaking a colder air mass. The other type of front right here is a stationary front. This is essentially meaning the two air masses are kind of just sitting there, not really one's overtaking the other. And a lot of times your wind is 180 degrees opposite. So you can see right here, the wind on the northern side of the stationary front is moving westerly, whereas the wind on the bottom is moving more easterly. The last kind of front is going to be an occluded front, which you can kind of see right here. Occluded fronts are where you really get your worst types of weather. And that's when a cold front starts to overtake a warm front. So, and denoted by this purpley area with both your semicircles and triangles. So as you can see, a warm air mass started to take over, then a quicker moving cold air mass came up behind it. And with this, you get a lot of embedded thunderstorms, a lot of rain, and it's just some pretty nasty weather generally. So with your fronts, you have what's called a frontal discontinuity. So those differences between the two air mass are your temperature, your wind speed, your wind direction, your humidity, and your pressure. So when you're measuring things, that's how you really determine when there's a frontal passage. A good example of this is as a underway OOD, one of the CO's standing orders was always whenever you had a wind shift greater than 20 degrees within an hour, you had to wake up the CO and let them know, or the commanding officer and let them know. And that's because typically when that happens, it's associated with a frontal passage, bad weather, possibly. And it's just something that the commanding officer wants to know. Now, with the fronts, I'm going to spend a lot more time on the fronts than the air masses because fronts are where we get all of our weather. So, for example, a cold front, which let me actually pull up a horizontal view of this now that I'm thinking of it, because this will really help to demonstrate. So as you can see, hopefully this pulls up well. So as you can see right here, a cold front acts as a wedge. That wedge is very fast moving and it very quickly lifts that warm air up into the atmosphere. And because of that, it's associated with your stratiform clouds, your stratiform clouds, the big, really puffy ones, your thunderstorms. Why can I not get back? There we go. Your thunderstorms or squall lines, your quick moving cold fronts are what really produce those really bad severe weather. Whereas a warm front is going to be much more gradual change because warm air is typically lighter and will be above cold air. So as it comes, instead of pushing the cold air like a wedge, it's going to kind of slowly overtake it and squeeze it out of the way. And with that, you don't get the large lifting like you do with a cold front. Instead, you get a much more stable atmosphere and low-lying stratiform clouds. So this is whenever it's just a dreary day, think, granted, I've never been there, but think Seattle. Always cloudy, always misty, always rainy. That's your stratiform clouds. It's just low clouds, light rain, showers all day, and then the clouds keep getting lower and lower, eventually possibly even to the ground where it would be fog. And then your occluded fronts, as I briefly touched on earlier, is a mixture of both. You get your stratiform clouds where with your thunderstorms in them. So that's where you start to get your embedded thunderstorms, things along those lines. And your stationary fronts, Not a whole lot of significant weather is associated with those. And a good way to tell for the winds with the frontal passage is you have backing and veering, which is essentially either the wind's going to shift clockwise or counterclockwise, depending upon what type of front moves. So if you look at this cold front right here, you can see the wind is roughly moving parallel to the front of the front, and then it's pushing behind it. So that wind is going to shift counterclockwise with the frontal, with the cold front passage. All right, so the next thing we're going to get into is our pressure systems. These are high and low. I really love high pressure systems because they're typically associated with good weather, clear skies, great flying, great boating, just everything good is good about high pressure systems. And this, as you can see, you have your isobars, or a line of constant pressure denoting this. So this high right here is about 1,012 millibars. I mean, does 112 mean anything? No, not really, but it's high. And then right here, you have your low pressure system. Low pressure systems typically indicate weather. At least the vast majority of weather is associated with your low pressure systems. And one important thing about these is the way in which the wind will shift around your pressure system. So for low pressure, it's an anticyclone. So that wind is going to be moving counterclockwise around the low. Think of a hurricane. That's where we get our navigable and our non-navigable side because of that wind direction, or the way the wind is blowing around that low pressure system. Then the high pressure system is going to be your cyclone, and it's going to be moving clockwise around that high pressure system. So when you're at sea, a good way to find a low pressure system is by using Ballott's law. You stick your back to the wind, left arm out, wherever your left arm is pointing, that's going to be the center of a low pressure system. This doesn't work really well when you're either inland on a small lake or a river, because you have a lot of structures kind of changing where the wind is coming from. And another important aspect with your pressure systems, particularly when it comes to the maritime environment, is a deepening low. A great example of this is the North Wall effect off of the eastern United States, particularly the mid-Atlantic. One of the reasons why Cape Hatteras is notorious for bad weather. So what will happen is in the fall and the winter, water retains heat a lot better than the air does, particularly when you're talking about ocean currents. So you have the warm Gulf Stream, which is always roughly the same temperature, and the area when the Gulf Stream is going to kind of kick off towards North Carolina near the Cape Hatteras and go out into the Atlantic, leaving room for the Labrador current, a very cold northerly current, to work its way down into the area in the mid-Atlantic off of New Jersey and Delaware. And what that's going to do is, as a low pressure is moving off of the United States, it hits that water, the warm water from the Gulf Stream, causing that low to what's called deepen. It gets lower. So as that cold air hits that warm water, it rises, which is what causes the deepening low. With that, the winds pick up, and they typically oppose the Gulf Stream, meaning very confused seas, very high sea states, very high waves, very strong winds. And that's why pressure systems are important. And a good way to know how deep a low is or how high a high is how close these isobars are to each other. The closer the isobars, the stronger the winds, the deeper the low or the higher the high. All right, let us now move on to anemometers, our measuring equipments. So the first one we're going to talk about is going to be a barometer, which we're going to be making a barometer, if I can adjust this light, similar to this. So what does a barometer do? A barometer is what measures pressure. And there are 4 main types of barometers, 2 of which are predominantly found on ships. Your 2 predominantly found on ships are aneroid and analog. Excuse me. Both work roughly the same. You have some type of, not necessarily a vacuum chamber, but a chamber of air which is isolated from the environment. So that way, as the pressure on the outside changes, so in here, there's the air should theoretically not be influenced or not change with the environment because of the seal. No air is going to get in or out. So this pressure is always going to be the same of when I first put the balloon on. As the air or as the pressure rises, it's going to push the cap of this balloon in, causing that the needle right here, which is a paper clip, to move up. If the pressure lowers, the balloon's going to pop out, causing the needle to move down. Your two shipboard or barometers use the same principle, just much more sophisticated than a balloon and a mason jar. And really the only difference between the aneroid and the analog is the aneroid looks kind of like a clock. It has an arm that moves around in a circle, where your analog actually has a drum of paper and a pen that moves up and down, drawing on the line. The only time I've really seen one of those was in a commanding officer's stateroom, and it was more as a centerpiece or a showcase. Then it still worked, but it wasn't what we used up on the bridge. And the other two types are mercury or water. Those don't work well because it's fluid. On a pitching, heaving ship, fluids don't do very well. So we stick to aneroid or analog. Now, in order to read these, you have to apply a bunch of correction factors. You can't just go look at what the dial says, be like, oh, it's 29.92 inches mercury. No, it doesn't work like that. So there are three main types of correction factors you have to add. One's temperature. Now, your more expensive or your higher quality barometers, you don't have to worry about the temperature because they use mechanics and materials, a phenomenon called bimetallic materials. So as one stretches, the other one contrasts and they offset each other. Your not so fancy ones, you do have to take into a temperature correction factor, because that is going to change the way the metal reacts. The next is going to be altitude. You may be thinking, okay, well, my altitude from sea level up to the bridge wing is 75 feet. Is that really going to make a difference? It does. There are barometer correction tables that you can find almost anywhere on the internet with a quick Google search. Or if you have a copy of Bowditch, the Practical American Navigator, has a whole bunch of tables in it as well. And then the next one is going to be instrument error. Every single barometer is going to have some type of error that's just built into the machine. There's no way around it, whether it's just tolerances from building materials or just one off from the other. But on that, the machine or the instrument should have what its instrument error is, so that way you can add it. And so how do you read it? You look at what the dial says, you calculate your temperature correction if you need to, you calculate your altitude correction if you need to, just by looking on the chart. All right, 75 feet, go over, all right, add 0.01, and then you add your instrument error. When you add all of those up, that's what your actually barometer reading is. Once again, the barometer is for pressure. The quicker you see that fall, you're gonna have some bad weather coming. We were moored up in Little Creek, Virginia. The barometer dropped almost an inch within 30 minutes. With that, we ended up getting 60-knot straight line winds. We broke 2 mooring lines, even with both anchors at foot. That was not a fun night. And luckily, whoever was on watch noticed that barometer falling very quickly and was able to start looking at some weather forecast and figure out what was coming. All right, so the next is going to be a thermometer. I'm not going to spend a whole lot of time on thermometers because we work with them at least on a fairly regular basis. The most common one is going to be a fluid bulb, where it's just little red strip, got a little bulb at the bottom, goes up, goes down. That's the most common type that I always see. There's also another kind that uses bimetallic strips. Those are going to be more of your dial thermometers as opposed to your just straight line thermometers. And with correction factors, depending upon the type, your fluid isn't going to have a correction factor. Your bimetallic strips may or may not have an instrument correction factor you have to add in there. I've never seen one with one, but it's not saying that you don't have to. And a word of warning, they don't always work. That being, what I mean by that is, if the temperature is below the range on your thermometer, you're not going to know what the temperature is. Coldest I've ever been was in the Gulf of Maine in the middle of January. The thermometer stopped working because the fluid was all in the bulb at the bottom. So all I knew it was colder than 15 degrees. That was very cold for a boy from Alabama. All right, next is going to be anemometers and weather vanes. Both of these are used to measure wind. So your weather vane is going to measure the direction of your wind. If the wind is blowing out of 010, the weather vane is going to point to 010. Now, a word of caution, it's only that easy if, and I mean if, you are stationary. If your ship or your boat is moving, just because your weather vane is pointing at a 010, that is not where your wind is coming from. That's where your relative wind is coming from. So if you wanted to use that wind, you'd have to do a maneuvering board, do all of your vector addition to calculate where your true wind is coming from. Or depending upon which, if you're on a large ship, that's the only way to do it, because you're not going to come down to dead in the water just to take a weather or a wind calculation. You're going to keep moving because it takes a lot of effort to get that ship going and a lot of effort to make it stop. So if you want to use your weather vane, either come dead in the water, see where it swings to, that's what your wind is, or break out your maneuvering board and start having some real fun. And the next is going to be the anemometer, which is going to be your wind speed. Same principle. If your ship is moving forward at 10 knots into a headwind, that's 20 knots, well, your anemometer is going to be reading 30 knots because it's reading both the speed of the ship and the wind, which a maneuvering board can compensate for that, or you can come dead in the water and see what your wind's doing there. Now, if you don't have an anemometer or a weather vane, there are ways in which you can estimate the wind speed. You can look at flags or you can look at the waves. And with the waves, the best way is going to be whether or not there are whitecaps, wind streaks, spin drift. There's a whole methodology to figuring this out. Now, it works better when you're at sea, because that way you actually have a large enough fetch or a large enough area for the wind to actually change the sea state to do this. So if you're on a small lake, just because you have whitecaps doesn't necessarily mean that your wind is 20 knots. The wind's probably higher than that because you only have 200 feet of lake. The best one is around the 10 to 15 knot range. If you see streaks, white streaks going in the direction of the wind, you know your wind is at least 10 to 15 knots. If you start to see whitecaps, you're around 15 to 20 knots. The bigger the waves get, the higher the wind is. Same with a flag. If you're in a small lake or a river and you see a flag that's almost completely straight out, you know your wind's upwards of 20 knots. If it's only half furled, then you're about 10 knots. If it's completely limp, it's not a good day to go sailing. All right, so, and from here, now we're going to kind of talk about how a forecast is made. There are, and I am running a little behind, so I'm going to kind of go a little quicker here. So how a forecast is made, I'm going to share my screen again, and hopefully y'all can see this. So this map right here is called a surface analysis chart. And what each one of these dots are a weather station. The most basic way in which a forecast map is made or a forecast is developed is using the station model. So every single one of these stations will report back to a central database or a central hub. And then a forecaster can look at this data and be like, okay, we got a whole lot of clouds over here. All the winds blowing in the same direction. We have wind shift or wind change right there. So I'm going to draw a front line right here. And they take this information and they just create this plot or this chart right here. Now there is a lot more to how a forecast is made. There are a lot more advanced techniques, a lot more advanced systems in play, but the basic model is with just weather or reporting stations. And even ships at sea, so every 4 hours aboard a Coast Guard cutter, we had to send weather back to the National Weather Service so they could even use it for the marine forecast. And now we're kind of going to get into the really nitty gritty, not so much nitty gritty, but the fun part, which is going to be the actual forecast. I'm a huge advocate for legal, official forms of forecast. Don't pull up the app on your phone. If you're planning a trip, don't pull up the app on your phone and be like, oh, well, Google Weather or Apple Weather says it's going to be sunny and windy, or sunny and not windy. That if something were to, one, it's not entirely reliable or entirely accurate. And two, if something were to happen and an investigation were to ensue, for all intents and purposes, you did not check the weather. So I love the .gov websites. So since we are the Sea Scouts and the Coast Guard and the Coast Guard Auxiliary, we're going to be talking marine weather. So the first one is the NOAA Marine Forecast, Coastal and Great Lakes Forecast by Zone. Best weather for any time you're at sea. You're just going to click your area. I'm going to do kind of where I'm from, up in Atlantic City, New Jersey. And right here we have our maritime forecast. So at the top, you're going to have a synopsis. So the forecaster is going to be giving you a bird's eye view of, hey, this is what's happening. So a high pressure system becomes more and more anchored in Western Atlantic and so forth and so forth. Then down below, you're going to have what he actually, or what he or she actually thinks the weather is going to be. So tonight it's going to be an east wind around 5 knots. It's going to give you the seas, the swell direction, the period, and any more amplifying information. So widespread areas of dense fog, areas of drizzle after midnight, visibility 1 nautical miles or less. And it's going to give you this for the entirety of the week. Now, this is great if you're at a ship on the coast, because it's going to know, hey, if I go offshore Atlantic City, this is what I can expect to see. Now, what's going to happen if I'm not? Say I'm in the middle of the country. Well, for that, you have the National Weather Service. You have your forecast. From here, you can go to local, graphical. I'm a huge fan of the graphical just because I'm a very visual person. And you have your short range forecast, so 12 hours, and you can kind of know, okay, similar map to what we were just looking at, but a little cleaner. All right, whole lot of likelihood for thunderstorms around this area, rain, high chances of rain. Look at these, and then when you dig more around into this, you can get your local forecast, and there's even a tab for it right there. The next one I'm going to advocate for, although yes, we are the Sea Scouts, however, the aviation forecast are very, very well. If you are in an area where there is an airport and you know the airport identifier, when you come to your forecast and your TAFs, which is a terminal aerodrome forecast, you can type in your airport's identifier. So at Atlantic City is going to be Kilo Alpha Charlie Yankee, KACY. And we're going to read the decoded, because if you were to do raw, it'd be very difficult to read. And you're just going to click the button, get TAF. And this is going to give you the forecast for around whatever airport you're at. And yes, it's not going to give you sea states. It's not going to give you periods, water temp, etc. But it's going to give you your visibility. It's going to give you your winds. And if there's thunderstorms or rain, it's even going to give you those. So air, weather, fog. Tonight, it's going to be foggy where I am living. So those are your good opportunities or good solutions for weather forecast. Once again, use your .gov sites, use NOAA, use the National Weather Service, because I'm biased, but they're the best. All right, so now we're going to talk about maritime applications of weather. Why? Because weather always changes over the water. Doesn't matter. Another quick sea story. So I was doing hoisting operations this past fall. We were going out, we were hoisting with our training boat, and weather was clear in a million where we were. And then all of a sudden we got word that there was a diver missing on a dive boat just south of New York. And we knew that there was what's called a marine layer, so an advection fog. So we had clouds pretty much all the way down to the surface. The boat was reporting half a mile of visibility on the surface. So we fly up there and we're like, okay, maybe we can help. We'll try it. And we shoot an approach to the water. We enter the clouds around 1,000 feet and we come to 50 feet below the water. Don't break out of the clouds. And we climb back up. The second we hit land, all the clouds disappear. Weather always changes over the water. So just because your terrestrial forecast or your land-based forecast is calling something doesn't mean it's going to happen. Another large or major thing that happens, particularly in the summer, is thunderstorms. When you might have a thunderstorm in the cumulus or the maturation phase. The second it hits water, the water is hotter. You're going to get a lot of thermal uplifting. It's very going to quickly build and become a much more worse thunderstorm. Then the next few things that we have to worry about in the maritime realm are winds and waves. Huge. Wind is what affects waves. So wind and something called fetch. How long of an area is the wind blowing over that water to make those swells and make those waves? The larger the fetch, the bigger the waves. The higher the wind, the bigger the waves. Whenever you get a wind shift, it's going to cause to confuse seas, because if the wind was blowing in the same direction, for days upon days, and then it shifts rapidly, well, now it's going to start creating seas in the opposite way, and you could get a bathtub or a washing machine effect. Then ice and spray. If you're out and it's cold, ice is heavy. Ice is very heavy. At about around 28, 29 degrees Fahrenheit is when seawater starts to freeze. You start getting spray up on your ship, you're going to change the nav arc or the naval architecture and the way that ship rides, and you could very easily topple over. And breaking ice is not fun. It is back-breaking work. All right, so with that, we're actually going to jump into building a weather station. So what we're going to need for this is a box. We're going to need some tape, trusty scissors, some balloons, and I didn't have golf balls or ping pong balls, so I got some golf balls, or practice golf balls. First thing we're going to do is we're going to make a barometer. Let me tear apart my current barometer. Oh, and we'll also need a paper clip. So the first thing we're going to do is we're going to take some type of jar. It could be glass, could be plastic. It doesn't really matter, just some type of jar, or some way we can isolate some air. And we're going to take a balloon. We're going to cut the neck off of the balloon like so. Let's see if I can. All right. Now we're going to stretch this balloon out, hopefully without breaking it. The last time I did this, I think I broke 2 balloons. But practice makes perfect. So what we just did here is we isolated all of the air inside this balloon from the outside environment. So now as the pressure rises, it's going to push down on that balloon, and as it lowers, it's going to pull up on the balloon. We're going to cut a piece of tape. We're going to undo a paper clip. The longer you make your paper clip, the more sensitive this is going to be. And then we're just going to tape the paper clip to the center of the balloon. Now, the paper clip should move with the balloon as it goes up, or as the pressure pushes the balloon in, the tip of this should go up. Then we're going to take a piece of cardboard and we're going to tape it to it just so we can measure where it is. And then hopefully we can see, I don't think so, but we're going to annotate with a pen where the paper clip is currently marked at. So that way when we set it down, we can come back. If the paper clip goes up in a few hours like that, you know you have a high pressure system. So we're going to write high up above and low down below, if you can see that. So we have high and low above the line. Now this is just measuring our relative pressure. We can't associate this with 22.9 degree or inches mercury, 30 degrees inches or 30 inches of mercury. We just know that relatively to the time that we first did this, the pressure is either going to rise or the pressure is going to decrease. Next, we're going to be making a weather vane. So what we're going to do is I'm going to cut off another piece of this box. And the weather vane, we got to make two parts to it. We're going to need some type of staff or stick, which is the part I'm going to make first. So I'm just going to roll this up. And then tape it shut. So this is going to be the pole in which we're going to mount our actual weather vane on. We're going to cut off another piece of the box. We're going to cut it into two pieces. What we're going to do with this is we're going to make an actual weather vane. So we're going to have a fin behind and just a flat piece of cardboard right there. The reason you want the fin on the aft part is so that way, the weather vane will actually point into the wind. We're trying to get our aerodynamic center past our pivot point. And you're just going to tape it on there. You might have to use a little bit of tape. Might even have to roll up some more cardboard and brace it down at the bottom like that. However, I think I'm going to be able to get it with just a few pieces of tape. We'll see just how right I am. All right. Not the most stable, but it'll hold up for demonstration purposes. Now, just so it actually looks like a weather vane, I'm going to cut a point at the tip of it. And then you're going to attach your arrow to your pole. And I forgot to bring a nail with me, but what you're going to do is you're going to take a nail and use that, or what I use is a nail. So first I'm going to tape over one side of my pole, and this is just going to give something for the nail to actually, some type of a structure for the nail to go into. You can even tape another piece of cardboard over it to provide a little bit more, and then you're just going to drive a nail right through it, which I'm going to use a pin since I was not prepared and forgot to bring a nail. And then as the wind will blow, that will pivot and point into the wind. Now the next thing which we're going to do is and that's going to get our wind direction. Next thing, we're going to take a ping pong ball, or I'm going to use these plastic golf balls, or practice plastic golf balls, which act very similar. And you're going to need a protractor. Now, I went to 4 different stores over the past 3 days looking for a protractor and could not find one. So I'm going to improvise a little. And you're also going to need a piece of string. I'm going to make my string out of my tape. This is going to make it a little easier for me to attach it to the golf ball. And then if you had a protractor, what you would do, I don't have one, you're going to attach the string to your protractor or your angle measuring device. And I'm going to use So the mark right there is going to be 90. And what's going to happen as the wind blows, this ball is going to move up. And that angle is going to be associated with a certain wind speed. And once again, there are chart, you can go through the math to calculate it, but we will be sending out a chart for you to use afterwards, so that way you can actually associate the angle of the ping pong ball with the wind speed. Now, the anemometer and the ping pong ball are only going to work well if you're not near any obstruction. So if you put it right up next to a building, it's not going to measure your true wind speed or your true wind direction. And for the ping pong ball, if it's not pointed into the wind, it's not going to deflect properly to actually give you a quasi-accurate wind direction. And so with that, I think we are going to open it up for questions.
Thank you, JD. That was exceptional. There are, for anyone who has questions, please use the Q&A box and type in any questions in there in the Q&A, and we'll do our best to answer them. But we do have some ready to go. So JD, what is your method for reading and sorting through all of the forecast data?
All right, so the method I like is I like to start big. So I will, let me share my screen again. So I start with my forecast maps. So I'll go to either my short range forecast or my surface analysis, and I'll just take a look at what is the large scale regional weather. Where are the high pressures? Where are the low pressures? What type of fronts are coming off of them? How quickly they're moving, where they're moving, just so I can kind of know, okay, this is what the big picture going on is. I'll then go to, since I'm in the aviation realm, I'll go to my aviation forecast. I'll look at, okay, what is my aviation forecast saying? What is my TAF saying? When is what type of weather coming in? What are the winds doing? What can I kind of expect for precipitation? And then I'll go to my marine forecast. Be like, okay, what's the waves doing? What are the swells doing? Are they changing? Are they building? Are they decreasing? And then pick apart the weather from there. So big.
Excellent. Sorry. One question is there an easy way to remember the different fronts and what they mean?
Easy way, I don't know of any acronym for it. The best way is, and this is going to show my southern inclination coming out because I hate the cold. So I always associated cold fronts with bad things happening because I don't like the cold. So typically your cold fronts are going to be your worst weather, your thunderstorms, your squall lines, possibly tornadoes, things along those lines, where your warm fronts tend to be a little nicer because warm weather is just much better.
Another question is, can an anemometer be connected to the weather vane to keep a ball in association to wind direction?
Yes, absolutely. Absolutely.
Okay.
Unfortunately, I was running a little short on time, so I had to rush through it a little, but you could very easily take the protractor, which I could not find at any Walmart around, and mount it either underneath or in front or to the side of your weather vane. And that way it'll help keep them together. Another thing you can do also is you can add a string or a flag to the back of it too. And that'll just kind of make it a little more visible, because where I put mine in my yard a few days ago, I had to really look for it.
Another question, how can you estimate wind speed without an anemometer?
So depending upon where you are, and I'm going to look up my book real quick just so I can actually give you some. Oh, where is Beaufort's? Is it Beaufort? So flags are a good one if you are inland or can see land. So if a building has a flag, that is a great way in order to tell how strong the wind is. A flag fully out and fully flapping in the wind, you know your wind is around 20 knots or higher. If it's only halfway flapping, it's probably around 10 to 15 knots. If it's limp, it's less than 10 knots. And I cannot remember off the top of my hand what the scale is, or the gentleman or the scientist who created this, but if you look at your waves, so I will try and show you a picture in Bowditch about it. But if you look at the sea state, so you can notice we have a few different things. We have whitecaps, which are just white parts of the line. You have spin drift, which is sea spray coming off of the waves. And then you have wind streaks, which are these right here, just white lines going in the wind. One in which I use all the time, particularly when I'm hoisting, are those wind lines, because the helicopter, we want it to be pointed into the wind as much as possible. So you look at where the wind lines are coming from. One, that's where you know your wind is. And if I have the wind streaks, I know I have at least 10 knots of wind on the surface. So if you're seeing white lines in the wind or in the water, you know your way or your wind's at least 10 knots. If you start to see whitecaps, you're getting closer to the 15 to 20 knots. When you start to see spin drift, hopefully you're in a ship and not a small boat, because you most likely there's a small boat advisor or a small craft advisory, but that's when you start getting upwards of 25, 30 knots. So looking at your sea state conditions are going to tell you a lot about what the wind's doing, as well as any type of flag on land or on shore.
Is there a way to tell if a front is coming without any equipment?
Yes, that's actually a really good question, and that is the clouds. So every cloud or every frontal system is associated with a group of clouds, and they have a progression of clouds. So take a cold front, for example. First, so let me back up a little bit. So clouds are associated, you have two main types. You have cumulus and stratus. Cumulus are your big puffy ones, a lot of vertical development. Stratus are your more horizontal ones. Stratiform clouds are rain clouds. Cumulus clouds are thunderstorm clouds, is a good way to associate it. Stratiform are also your warm front clouds, whereas cumulus are your cold front. And then you also associate your clouds with height. So you have cirrus clouds, which are way in the upper atmosphere. You have your alto, and then you have your low clouds. So you have high, medium, and low. As a front is coming, you're going to get those clouds coming down. So if you start to see really high cirrocumulus clouds that then turn into altocumulus that then keep getting lower and lower and start building, you know a cold front's coming. If you see the same thing with stratiform clouds, your stratiform clouds starting up really high, starting to come down lower and lower, you know a warm front is on the way. So look at the clouds. Stratiform equals warm, cumulus equals cold. And with that, your cold fronts are typically very short, very narrow. They could be as quick as 10 miles and 10 to 50 miles, whereas your warm fronts are hundreds of miles long. They could be 200 to 700 miles long. So how quickly those clouds come and come down is going to also depend upon what type of front. Warm front, they're going to come down slower. Cold front, they're going to come down quicker.
So we have a request. Can you explain air mass again?
Yes, so a air mass is a large volume of air over a large geographic area that all has similar properties. So the temperature is going to be similar. The humidity is going to be similar. The pressure is going to be similar. And when I say similar, it's going to be in relation to another air mass. So for example, an air mass coming off of central Canada is going to be very cold and very dry, particularly if it runs into an air mass coming off of the Gulf of Mexico, which is going to be very wet and very warm. And when those two air masses collide, that's what's going to give us the front. So it's that difference between those two air masses which is where we get the weather. So yes, at the center of the air mass, so say we have an air mass extending all the way from British Columbia down to Oklahoma. The air up in British Columbia might be 40 degrees, where the air in Oklahoma might be 50 degrees. But when you compare that to an air mass coming off of the Gulf of Mexico where it's 70 degrees, the 50 and the 40 look pretty similar. Hopefully, let me know if that doesn't clarify or that doesn't make sense.
We have another question about the, I've always mispronounced this, Barometer wind scales.
That's the one. Thank you. What's the specific question, or do they just want more info on?
I think they just want more info because that's the extent of the question.
Okay, excellent. So the wind scales are a way to estimate the winds without a anemometer or a weathervane, just by looking at the current conditions. Okay. And if you were to do a quick internet search, you could associate or find the pictures with the specific wind. So let me pull these up in my book. I just had it flagged. And I'll just give you some brief examples of some of the lower scale ones. But these only work when you have time for the fetch to fully develop. And by that, I mean, if you are on the windward side of a lake where the wind is first hitting the lake, you're not going to see the conditions required for the Beaufort scale to actually take effect. You're going to need to be on the far side of the lake in order for it to happen. Where did my picture go? Ah, here we go. So for example, a wind speed of 1 to 3 knots, you're just going to see light ripples and appearance of scale, no foam, no crest, nothing like that. When the wind gets up to 4 to 6 knots, that's when you're going to start seeing small wavelets, crest of glassy appearance, not breaking. The 7 to 10 knots, large wavelets, crest breaking, scattered whitecaps. 10 or 11 to 16 knots, small waves becoming longer, numerous whitecaps. 17 to 21 knots, you're going to have moderate waves taking longer form, mini whitecaps, some spray. So it's a way to take the observations that you're seeing and associating that with a certain wind speed. Now, few whitecaps to some might be a different number than others. So a lot of that scale is going to be based on experience. So I encourage you, when you're actually out on the water, look at the environmental conditions you're seeing. Look at what the waves are doing. Look at what the flags are doing, what the spray is doing, and then cross-check that with your instrumentation. So that way you can know, okay, when the wind's coming from this direction at this wind speed, this is what I'm seeing. And then the more you do that, the more you add to your repository of knowledge. And then the quicker you can look out and be like, oh yeah, it's roughly 10 to 15 knots. Okay, we're good, or we're bad, depending upon what type of craft you're in.
So here's a question on puffs, and it's a little complicated. So hopefully this makes sense. Do puffs, depending on body of water, change how they act? And the qualifier is the questioner is a sailor in Chicago and wonders if puffs would be different in, let's say, sea bodies in California. So I guess the California coast and the Pacific versus the Great Lakes.
I'm confused as to what they mean by puffs. I've never heard that term.
Okay. If they want to ask a follow-up, they can, but let's press forward. What weather is the best to go sailing in? And this should be a very interesting one because that could vary.
Windy. Assuming you're in a sailboat. So if you're in a sailboat, you want wind. You want those isobars to be really close together. You want strong wind. I would encourage you not too strong, because stronger winds for a longer period of time do cause larger sea states. However, windy is always better for sailboats. For non-sailboats, I still consider a diesel-powered ship sailing. Love me or hate me for it, I don't care. I always like calm. Well, okay, I lie. I was the weird type. I love turbulence in aircrafts, and I love large sea states just because I'm an adrenaline junkie and weird. When green water comes over the bow of a ship, phenomenal. I sailed through Hurricane Sandy on a search and rescue mission on a 378-foot cutter. We were getting green water all the way up to our gun deck. Oh, it was probably 20, 30 feet over. And I know that the Bering Sea sailors out there are probably like, oh, that's nothing. Wait for the 70, 80-foot waves I've been in. But calmer is always better, unless you're weird. I don't encourage you to go out in high sea states, because then people like me have to come out and get you if you get yourself into trouble. No one ever gets into trouble on a nice calm day. So calm, always better. If you're not sailing, no wind. If you are sailing, you want some wind, preferably little to no waves.
So did you study weather in college, or did you pick this up in flight school?
No, I picked this up as a combination of being aboard ships. So in the Coast Guard, as part of your deck watch officer qualification, you have to study and show practical knowledge about certain aspects of the weather. And then in flight school, they really harp on it, and you go into a lot more detail, just because weather and aviation are intrinsically entwined. And I would even argue weather and sailing is intrinsically entwined, because the sea is not dangerous, but it is very unforgiving. And it's the weather is one of the major factors that make that very unforgiving, and that weather can change oh so rapidly and oh so quickly.
Excellent. So one last, we have a thank you. There are multiple thank yous. For those wondering about the YouTube channel, it's YouTube and it's Sea Scouts BSA. And our Facebook page is, facebook.com/Sea Scouts BSA. And we will have the videos posted there. And we appreciate everyone's time. And next month, we have another session, and we'll put up the slide for that right now, on celestial navigation. And this is a ton of fun. I am looking forward to this myself. And that will be on June 23rd at 2100 Eastern, 1800 Pacific. And stay tuned for more information. And we'll have the links posted to that very, very soon. And so everyone, thank you for tuning in, and stay safe, and we'll see you all soon. Take care now.
Thanks, everyone.